So hi everybody. So in this presentation I will show you how you can program an IPv6 enterprise network with IPv6 segment routing. So enterprise networks differ from ISP networks because they are first smaller. They have much more endos. What I mean by endos is laptops, servers, and so on. And the enterprise IT typically control typical network devices like switches, routers, and middle boxes, but also endos, at least partially. And you also have business rules that favor some applications over others. These enterprise networks have a lot of diverse requirements. For instance, quality of service to run voice over IP, or access control or middle boxing to go through a set of given middle boxes. And of course, SDN is a possible solution to tackle those kind of problems. But, well, I do not really explain in details how the SDN works. I think you all know how it works. You have a logically centralized controller, and you typically use OpenFlow or another protocol to program the switches. But I state that it's not the best strategy to go with the enterprise networks because, well, first, if you want to have per flow control on the network, you have to install per flow rules and hence have state explosion on the network devices, each network device on the network. And second, you don't have kind of exchange with endos that can provide additional information about the applications that they are running. Another point, so I will use IPv6 segment routing to solve this issue. And so my point is IPv6 will eventually come to enterprise network, so it's not that unrealistic. And I want to instantiate this SDN vision in IPv6 enterprise networks. So IPv6 enterprise network typically will run an IGP protocol that will distribute routing information, and this will allow traffic to go through the shortest path to the destination. Of course, the shortest path is not always the best choice. For instance, if you want to do traffic engineering, you may want to use, for instance, here, the lower path on the network. How do you do that? Well, you can use IPv6 segment routing, which is a modern source routing solution that allows to encode inside the packets the path that you must take inside the network, not the whole path. Here, I have encoded the bottom path by simply putting the IPv6 addresses of router 4 and then the IPv6 addresses of router 6. And it will follow the shortest path towards each intermediate nodes inside the network, and then the shortest path towards the destination. With IPv6 segment routing, you can enforce any path inside your network. And you allow the endos to specify this path. But still, allowing directly the endos to specify which router you cross is not really the good strategy. You may want, because the endos may not have knowledge about may certainly not have knowledge about the topology of your network. So what I will put, what I will put instead is a path, is an additional level of indirection. Note that I have said that OpenFlow requires state inside the routers. To enforce this path, I didn't add any state inside the network devices. And so this level of indirection, we add as the list of intermediate nodes a path ID that actually match the router 1, and the router 1 will translate this path ID towards the real path that you must take inside your network, here 4 and 6. This level of indirection allows you to change the path behind the endos if there is a new router in your network or if you want to react fastly to a failure. And it works as I've said before. But still, how do you want an endos to know the path ID to use? Well, it has to communicate to a central unit that will tell him which one to use. And how will it communicate? Well, we have chosen to use DNS to do that. So why DNS? Because it's a widely deployed protocol, and because we can extend it easily by adding, for instance, here a requirement of the application. This application wants 8 milliseconds of latency, and it sends it to the DNS resolver, which is, in our case, also the SDN controller. The SDN controller makes some computation and return a path ID and install inside the access router the mapping between the path ID and the real path to use inside the network. So this is how it works. And this is why we want to do it. But let's dig a bit into the details. So I've explained that you have a client that requests some requirements to the SDN controller, get back a path ID. But this only works on the client side. For the server side, there is no domain name to query. So to use to query the DNS resolver, you have to use another thing, and we have chosen to use the path ID because the path ID is actually inside the packets, encoded inside the packets and arrives to the server. So the server can know the path ID to send to the SDN controller. The SDN controller will know to which flow it corresponds, and well, it can pass additional requirements. Here I didn't put it, but it's possible. The rest of the workflow works the same way as the other side of the client side. Now let's dig a bit into the SDN controller component, because of course the DNS resolver is not exactly the SDN controller. They are separated, and there are other modules to make that work. The first module that I will cover is the network state daemon. The network state daemon is actually listening to what happens in the network. How does he do that? He listens to OSPF advertisement, for instance, that allows it to know which router, which link is up or not, and also with OSPF-T extension, current bandwidth utilization and latency of the links. So when an end host makes a DNS request to have 8 milliseconds of latency to server.com, he makes this request to the DNS proxy, which is the interface between the end host, the DNS resolver, and the SDN controller. The DNS proxy will transfer the request to the DNS resolver. The DNS resolver is regular. There is no modification inside. It's simply the company DNS resolver. And so it will get back the answer. The DNS proxy will then send all the information towards the SDN controller, which makes some computation, generates a path ID, install the mapping between the path ID and the real path inside the access router, and then return the path ID towards the DNS proxy, which will finally send back the reply to the end host. And that's how the end host can know the path ID and then go through a given path inside your network. So that was about the detailed design. Now let's see how well it performs. We have, of course, implemented a prototype. This prototype is composed of two components. We had to modify the IPv6 and routing implementation to do that, but it's already merged inside the Linux mainline in version 4.14. And we also had some code for the controller and the application API code, which is available online. The link is also in the paper if you want. So the first measurement that we have done is load tests on the SDN controller without any DNS interactions or OSPF interactions. We have tried to send a lot of requests and see how well it performed. The measurements were made on a low-end machine, and you can see that, well, with 2K requests, it's very well. You are below 1 milliseconds. 4K requests, it starts getting a bit worse. And 10K requests, it's completely garbage. But we are in a case with one single thread inside our SDN controller. I will show you just after what is the result with more threads. But one thing to remember here is that in our campus at UCL, we observe like 1K requests at peak rate, 1K, DNS requests at peak rate for after all, an enterprise network which is 33,000 people wide. And so even with one thread, we are already above these requirements. But what happens with more threads? So you have, with 10K, we are also in 10K requests per second here, but we vary the number of threads. One thread, it's the same curve as before. Two threads, you can see that you can accommodate directly with half of the requests, while the others experience a queuing delay. And with 4 threads, you almost have 80% of the queries that are handled, that are handled directly. And so, next experiment, we try to measure the latency of the DNS requests that between the DNS request and the DNS reply that come back to the endorsed. And for that, we emulated the following network in a Mininet-like environment. And we compare it with the regular DNS requests, which is made to a regular DNS resolver. And we observe one additional RTT plus 5 milliseconds. So this additional RTT is actually the time to install the mapping between the path ID and the real path inside the access router, and then the confirmation of the installation of the path. The 5 milliseconds are believed to be due to the virtualized environment. Why? Because the controller is taking less than 1 millisecond, as we have seen before. So to confirm this intuition, we have increased the delay between the access router and the controller, and we've seen that with 20 milliseconds of RTT, we get 25 milliseconds of difference. So it confirms what I've said. Last experiment is about failure recovery. So one of the advantages of this architecture is the use of IGP, because IGP is a distributed protocol that recovers fastly from failures. And so we are in a position with a request of 8 milliseconds, a path that was produced, and a failure happens. The link goes down. What will happen first is the IGP convergence that will produce another path, so that will preserve the connectivity, which is the most important. Of course, it violates the constraint, but at least you preserve connectivity first. And finally, the controller will realize that there is a failure and will improve the solution. It cannot go back to 8 milliseconds because it's not possible in this case, but it minimizes the delay at least. So let's sum up with this presentation. I first presented why we are doing this. So we want to involve endos in a way that preserves a stateless network core inside an enterprise network, because an enterprise network has a lot of endos to deal with. I've presented the detailed design, and we also made a prototype evaluation, whose prototype is available online. Yes?
Thanks for the presentation, Jeff Nosh. Why did you use DNS? I mean, we had 2 years of discussion and figure out that at least DDT is probably the best solution to do things. DNS messaging is fixed. You cannot reuse your resolve library anyway. You need to change everything. So why DNS?
Sorry, did you...
Lisp DDT scales better. It's much more suitable for...
I didn't understand the alternative.
Lisp DDT, distributed database, RFC 8111.
Lisp LDT?
DDT.
DTT.
We should probably take it.
Yeah, I'm not aware of this library.
So every time you need to convey new type of message in segment routing, you need to hug DNS again, right?
Sorry. So, yep. So there is a DNS extension to add the requirements of the applications, and there is also a DNS extension to carry the segment routing list, which is in this case the path ID.
So what if you need secondary paths, you need association to primary? You do what we've been doing in transport networks for 20 years. You'll keep hacking DNS.
So if you want another path, well, it depends. You can remake a request to the DNS resolver if you want a new path and you weren't aware before that you wanted a new path. But you can still request it at first, a set of a given path that you want.
How do you translate semantics of transport path into DNS messaging?
These are IETF considerations. We are actually trying to push an IETF draft currently about that DNS extension.
Good luck. Thank you.
So basically, this is a hybrid network, right? So what's the advantage of your work compared to the pure SDN network? Because we are talking about so many good features about SDN, centralized control, and the big view.
So what are the advantages? This is still centralized controller. So there is still a centralized view of the network. The endos doesn't have a centralized view of the network. They have only requirements that they transmit towards the controller. So this stays. And what doesn't stay is actually, well, what changes is actually that the endos are involved and the endos can transmit their requirements, and they can also use IPv6 element routing, which requires less state inside your network. Did I answer your question? Yeah, sure.
Hi. I'm just wondering, where do you, what do you use? So you're basically pushing flow rules and then you're pushing some.
Sorry, I cannot hear you. Can you speak more closely to the...
Oh, sorry. You're pushing flow rules into the switches, and then you're using some identifier to in the packet itself to route the packets.
Okay, so
right?
These are not switches, they are routers.
Ah, okay.
So this is plain routers.
Okay.
Yes.
How do you bind prefix to the path ID? When you look up destination IP address, you need to know which path it goes to. How does the binding happening?
Binding between the path ID and the path?
So you've got your destination.
Yeah.
It should follow a particular path throughout the network.
Yeah.
So you need to have a binding, someone to tell you, this is the prefix, and this is the path ID I need to use to resolve it over. How does it work?
So the application has to do that with a socket option API.
So you make application aware of presence of segment routing?
Of the path ID and segment. This API is actually already in the Linux kernel.
There are no applications on doing it. You could have anything in APIs level, but someone has to use it in order to make it work.
Yeah, sure. But there is also support for other applications, limited one, where we actually give the path ID as the destination address, and we make the translation inside the access router. It's more explained in the paper.
We have time for one more question, if there's a quick one.
Really quick, something I don't understand, for instance, on that slide is why in your example you involve the client at all. So why do you involve the client in this picture, right? Because the client makes a request to the DNS, well, it says the end controller, and the controller actually installed the path at the end. And it's just a path ID, so the client actually doesn't even know the path, right? So you could actually completely remove the need, I guess, for the client to be involved. Or is it more for the client just to say that I don't like the current path, give me a new one, but I don't care about which one, and I'm just doing it via DNS request? Or I'm probably missing something. If it is too long, we can take it offline as well. But,
maybe short intuition of that. The problem is, how do you match the packets here to the path? Well, how do you do the classification then? With plain routing tables, you cannot do it. What you could do is like an alternative solution with an open flow that making a strange classification, and then or P4 maybe more likely, to add yourself the segment list.
All right, let's thank our speaker.